Very welcome to the very first session. I hope you don't expect me to show you how to make amazing noise, because it's really not about that. It's more about understanding what the hell is going on and being able to verify and understand fully what a synth can do for you. As far as the generic regular things, patching synths, patching drums goes, that's all over the place. You can learn that from YouTube, from books and all of those. But what we're going to do here is something else. We're going to dig into the depth of it, and the oscilloscope is our main beast here. Yeah, because that's the only way we can truly verify what's going on. And what you have, at least as far as my appreciation for modular is concerned, what you really have is the need to find the anomaly. Yeah, so, and you see, because with a digital emulation we can do all these things in a quite similar fashion, but they just don't have the kind of anomalies that modules do. Right? And in order to find the anomalies, indeed we have to stretch the string. You know, we have to work it in unusual ways. Yeah? Okay, so that's the bit of an intro. I have a few topics here. I will be making sure that you guys keep acting interested, hopefully. Stop me, accelerate me, slow me down. I'm here to help you, so make sure I'm dealing with the right things. Cool. So first of all, DC-AC, yeah, direct current, alternating current, very important distinction. Essentially all the sound is alternating current. I won't go too much into the basics here. I have an oscilloscope here. Let's see if that is still working. So what am I supposed to have here now at this stage is some kind of a signal. Let's see if that is still working. Okay, yeah, there is a sine wave right there. Yeah. So sine wave is an alternating current signal. And before we get into DC, I will already introduce some things about the oscilloscope, okay? So oscilloscope is made such that you can actually use it for measurement. So it has these fine lines that can help you estimate the exact voltage. Yeah? So it's an exact measurement that we're looking at. Obviously you guys might not see it, but the point is that you can set the resolution vertically and horizontally independently. And in this case what I have is I have two traces, I have two channels. So now I have this sine wave in the first channel, and I can already read out what is the output range, the voltages that this oscillator is giving me. You see, because I have a direct measurement of the output, and in this case I have 5 volts per division, so this is a plus minus 5 volt sine wave. Yeah? So you know that is the voltage, and this is fairly important because you'll see that different modules respond to different voltages. So we'll get talking about that in a minute. And then what I'll do now is on the second channel, you see what I have here is a DC voltage, so it's flat. I can control it with this dial, and I can go from minus, let's see, it does seem a bit inverted, yeah? That's funny. So I go from minus 5 and a bit to plus 5 and a bit as well. Yeah? So I have the same similar range. Now, the range, the actual maximum range of these synths is plus minus 12, and this has to do with the rails, because the power supply gives plus minus 12. So actually you see that there is quite a lot of scope for abuse, if I may. So the first question would be, how do we get a higher voltage, both DC and AC? And one of the things you can do is just get a proper amplifier, like a microphone preamp or something that has a larger gain. But actually there are a few tricks that we can do as well. So what I'll do now is essentially get this DC voltage that you see on the second channel back into the same mixer channel. Okay, so that's this. Just a second. Because what I can do actually is I can add up these voltages as well. right? See, so now I've gone way below -5 volts. So, and obviously with this technique I can go above as well. You see, there I am at almost 10 volts. And what I can do is I can do this one more time to really stretch it, because what you will see is that modules tend to respond in very different ways in this sort of non-official voltage range. Yeah, so it's quite exciting to be working with these. Okay, any questions about this so far? Let me just get my notes visible as well. Okay. So we have this, so briefly about how I've done this. Essentially, there are very few modules that will give you a DC voltage just like that on a pot. This matrix mixer that I've got here, what it does, if the first channel can give me DC voltages essentially. Yeah? If I don't send an AC signal into there, I will get DC voltages. And matrix mixer is a really funny beast because it can allow you to do a lot of feedback loops and other kind of unorthodox things. Because technically the main difference between what you can do theoretically already between analog and digital is that in analog you can actually produce a feedback loop. In a digital system where you have samples running, you always have at least one sample delay, no matter what, because you cannot compute a full cycle. You know, actually you could probably make a simulation that you compute maybe 10 cycles or something, but you cannot do this infinitely, which is something that you'd have to do if you want to run the same thing in a loop. So there's always a delay, and with modular system, with analog systems, actually there is no problem with this. And when you put things in feedback loops, these moments are the ones when things start freaking out. And you know, you get the anomaly of the things. Okay, so we've talked a bit about DC AC, we talked a bit about the range. Let's just see how this range business works for us. So what I'm gonna do now is I have a filter here. This is an SSM type filter, and if I increase the resonance, what I get is self-oscillation. Yeah, that's what you see. And then I can change the frequency. Now, I haven't talked yet about triggering of the oscilloscope. It is an important feature that allows me to essentially have this wave fixed like this. It really depends on the oscilloscope that you have in terms of how do you set it up, but in essence, you see that the waveform is not moving back and forth, it's actually fixed in time, so that's quite handy. So what I can do actually now, because I have an oscilloscope, I can also measure the frequency of this signal. Yeah? The way I do this, I'm going to take the lowest frequency that it does. The way I do this is as I look at a full cycle. So the trigger is currently set up such, I'll make it a bit more accurate, that the cycle begins exactly on the 0 line, so I can read where the cycle begins again. Yeah? So this for me is currently, let's say, 2.5 divisions, just slightly more than that, and 1 division is now 50 milliseconds. Yeah? So I have 2.5 of those, which means, let's say I have 130 milliseconds. Oh, sorry, I said the wrong thing, sorry. That's 1, 2, 3, 4 and a bit. Yeah? So that's about 230 milliseconds is the duration of one period. Yeah? So this is about 4 point something hertz, just less than 5 hertz. It goes up and down 5 times per second. So actually what you see here, I know now for a fact that this filter goes down to 5 hertz. And well, actually this oscilloscope does measure frequencies, but for this one it just says less than 10 hertz. Now if I push up the frequency completely, well, now I can just use this reading. I mean, I showed you how to do it manually, but it actually says 16K. So this oscilloscope, oh sorry, this filter goes between about 5 hertz to 16K. Okay? Now, the interesting thing is that obviously I have voltage control of the filter frequency. Is that everyone happy with that in terms of what that means? Yeah, you have some basic understanding, yeah? So now what I want to show you is the fact that if I play with this, I'm still looking at this DC voltage on the lower one, yeah? So I'm going to use this DC voltage to control the frequency of this filter, okay? Now it's all zeroed out, so I'm going to try and do the lowest possible voltage that I can get out of this funny thing, okay? Yeah, there it is. So actually we're quite low now. We're actually below 10. We're just against minus 12 volts. So now I can increase the attenuator for voltage control input on the filter. So what I'm likely to see, yeah, there it's gone already. So actually now I'm pushing the frequencies lower than what the pot allows me to do. So the voltage currently is too low. So I'm going to up that a bit. Okay. Let's start with 0 volts. Okay. Right. So you see, actually I've already done it. Now if I decrease this voltage, I'm getting lower frequencies. So if I'm really interested what this frequency is, and I am, I'm going to change the vertical or the horizontal division. Let's go to 250. So this is now 250 milliseconds. So actually see the duration of time as it draws the line. Okay, so what I see here is that as I decrease the voltage, obviously the frequency is going down, and then at one point it just stops. And there you see that actually now I've got to a point where I get one impulse. This is really slow. This is so now I have 1 second like this. This is about every 2 seconds. So I've got this filter down to 0.2 hertz. Yeah? Which is quite powerful. And now I can check the upper border as well. Let's do that. So now I'm gonna get this voltage, control voltage, as high as I can get it. There it is, plus 12. And now I can read it out. This is actually 62 kilohertz. So you see that the actual design of the circuit gives you much more than the actual system, you know, is designed to let you do, because you see I have had to hack my DC voltage to go full range, and then I can get my filter to do these things. Now, why is it meaningful to have a 65 kilohertz filter or a 0.2 hertz filter? Well, just you can have it, yeah? Now, the funny thing is obviously that each filter will do this differently. Yeah? So we can I have another one here. Just you can have it, yeah? Sorry, is that me, yeah? That's great. Okay, so something has happened in the meanwhile. Okay, so what I have here now is another filter. Let me see. Maybe I should not talk about that. We will have a class in the advanced course on filter design. The important thing is that filters are designed with completely different strategies. So, I mean, my personal set, this is about a fourth of it. I have about 15 different filters. Just because, and most of them are dupers, by the way, just because they are cheeky enough to, just steal other people's designs. Because you can't get to all these designs otherwise. They're just buried in old synths. And that's the really exciting thing, because once you start to really work the electronics in there, then you will find that all these filters respond in completely different ways. Yeah? I mean, what you had seen there a second ago was this one impulse, and then nothing for 2 seconds, and then another impulse as well. This is typically an anomaly that only this type of filter will deliver. Okay, so we should talk about range. Important terms are unipolar and bipolar. So what you've seen here is that I've produced a DC voltage that was that is potentially unipolar. Yeah, I can go below the zero line and above the zero line. And what you've seen is that I've driven this filter's frequency with the bipolar signal. Yeah. The important thing to understand is that some modules will not allow for bipolar input, or at least they will not do anything. Yeah. So in a way, it's really important to discover your modules. I mean, I'd be really interested in, you know, like 3 modules compositions. You know, how much can you actually hack a single module? Because you're likely to be able to hack it in many different ways. Cool, so we've done that, unipolar, bipolar. If there's any questions, just ask, please. Okay, so one thing that I just briefly want to show you in terms of understanding the hackability of things is joining and splitting, yeah? So I assume you understand the principle of mixing sounds. As far as the voltages goes, this is adding voltages, yeah? So what I'll now do briefly is just, this is now my output. Okay, I'm gonna just play 2 oscillators into my mixer. Okay, so we've got, that's 1, 2. Okay, you hear the 2 sounds. There is the plot of that. Now, what you might be asking is, you understand we have splitter cables. There are splitter cables. This is, what is this called? This is stackable. Yeah? So you might ask, why am I using a mixer? Can't I just join these signals? And the answer is, if you want pristine sound of certain modules the way it was designed, no. If you want to break things, yes. So it's a technique that can do a lot for you. Now technically, we have splitting and joining as an option in terms of a signal flow. And as far as splitting goes, you can do it and the other way around. The thing that happens is that you lose some voltage. Yeah? So I'm going to briefly demonstrate this. So let me just say that this, replace this with a stackable cable. So now I have them mixed together. Well, actually I should do the right thing and go full volume. Yeah, now they're mixed together. And now they're joined together just by connecting the 2 dots. You see, so I've lost some, this is mixing, and this is joining, so I've lost some volume. Now, as far as the sound of this goes, you probably agree that there is not much difference. However, if you have complex patches, if you have modules breaking already, they can break each other like that as well. So because essentially if you join them like this, they become interdependent in a difficult to explain fashion. It really depends on the modules themselves. Sometimes you will get that this does not make a difference, but sometimes it might make a difference. Yeah. So if you want this interdependency and you have sufficient gain around your system, you can do this joining. Now the same thing goes for splitting. Added to that, if you want to split things in a pristine way, you need buffers, yeah? Active multiples, which will make sure that the modules stay isolated as much as they do in such a situation. Okay, so that's joining, splitting. Now, in terms of gain, let's try to analyze. Let's see. I have a thing here which is dual voltage control crossfader. Yeah? So what that means is that I actually have a CV control that will change the amplitude of 2 inputs that are mixed into a single output. So there is a gain stage in there, and just to see how I'm getting on with these things, I'm gonna try to analyze this. Let me just use the first channel of the oscilloscope. Yeah, so now I'm looking at the output of that, and what I will do first of all is I'm gonna send it voltages. Worth knowing, so you've seen me play with the DC voltage on a CV input. which is the regular thing to do. However, DC signals will normally be throughput if you put them into the input of a module. So unless the module is made to filter DC out, but most modules don't do this. It's possibly worth showing you this now that we're here before we get to this point, is that if I send a DC voltage, so just make sure you see this as well. This other thing, yeah. So if I send a DC voltage to a filter, so this is now gonna be the output of my filter, actually just like this, yeah. So I'm gonna be sending a DC voltage to this filter. I'm gonna make the Q not self-resonant. We need some input here. You see, actually I'm getting it through. So I'm gonna send a bipolar one. So you see the first trace here is the output of the low pass filter here. So if I send a DC voltage through a low pass filter, you see it's actually tracking it more or less. Sorry, that's the wrong knob. It's tracking it more or less, but there is some funny anomaly happening. You see, it's actually intermittent. It's not even, we'll probably even listen to that. Let's listen to that. Do we not listen to that? This is that. It might be very soft, so we can't really hear it. Well, anyhow, you see that it's already doing something strange. It has these intermittent clicks there, but it's actually throughputing the DC voltage. So it is important to understand that DC theoretically is 0 Hertz signal. Yeah. So in that sense, you can predict that a low pass filter will allow it through. However, if I take the high pass output and now change the incoming voltage, well, you see that the anomaly is there, but I'm not throughputing DC voltage. No? Okay, so actually, therefore, it might be worth, if you have, especially if you have a few modules only, figure out, do they throughput DC voltage? Figure out what is the range. You might find that, this filter did respond to minus 12 volts on its input. It still made a difference, you see. And obviously, you could argue that, at that low frequency, there's not much we can do. But when this becomes part of the anomaly, then indeed it will make a lot of difference. Okay, so we have this AC/DC signal thing going. So let's see how my voltage control crossfader deals with that. So what I have here now is a DC voltage going into this crossfader and coming out on your screens. Yeah, so you see it's -5 +5 still. So that's all fine. And what I'll show you now is that if I have a voltage control here, what I will get, let's see, is essentially attenuation of that signal. So you see, I'm actually lowering it and making it higher with the other signal. So if this is full positive, I can actually get a completely different range. Okay, so I know now that this crossfader is happy with DC in both CV inputs and otherwise. So let us briefly examine what happens if I send. Well, let's just first see. So now we know that the 0 Hertz passes on both inputs. Let's figure out what is the maximum frequency, because you will have this, that some CV inputs just don't go above a certain threshold in terms of frequency. They won't react to very fast things. So what I'm going to do now is put a DC voltage into the input. Yeah. So that's that. Let's keep it +5 volts. And then I'm going to put an oscillator into the CV input. Yeah. So now I'm essentially controlling the gain of a DC signal with a sine wave. Okay. So and it's actually already quite high frequency. Can I read it here? Let's see what's happening. So just the division here. Okay, so there is my sine wave happening somewhere. And then let's just see if I can make the trigger work. Okay, trigger's fine. The thing is, with this oscilloscope, I cannot go higher than 5 volts. So in terms of division, that's my max. But what you actually see here, especially, maybe I could attenuate this signal. Let's see, what am I doing here? Well, obviously with this CV I could do. Okay. So there you go. Actually, what's happening here is I'm getting a rectifier. Now you see, so I'm not amplifying the lower bit, it just sticks to 0. That's fine, but the question, the original question is, how high of a frequency can I input into the CV input? So here am I trying that out. So it's still coming through, there it broke. Yeah. So I have here 3.2 kilohertz. Yeah. So let's go a bit higher. Okay, that's already broken. Just trying to get to the highest frequency before it breaks. Maybe I have more luck with this one. Okay. So you see, as I increase the frequency, well, actually this one now goes to 11 kilohertz. That looks quite promising. Let's try the pulse wave, because this is the maximum of this one. But with this one, I seem to be able to break it. So this is pulse width, because this one goes much higher. Well, in any case, you see, it doesn't go to full range. I mean, I should be able to properly test it. Let me just see, I can just do that with another CV. Okay, so CV there. Is that still not sufficient? Okay, so now I've got to still at 3.2 kilohertz. 1, 10. This number is not great, to be honest. Let's just see. Okay, let's try with this one. Well, because I managed to break it a second ago, but this one is actually quite robust, seems. So I go to 3.2 kilohertz now. 37, that's the CV here. CV1. So I'm not quite managing to break it as I did a second ago. You will find that sometimes you get intermittent behavior as well from these things. The nice thing is that they normally don't break. You can normally get away with quite a lot before they actually do something wrong. Pulse, frequency. Yeah, I'm at 11K now and it's still fine. Let's see, can I push that a bit more? 13K, 20K. Okay, well, now I've managed. I'm not sure why it broke a second ago, but now I've got it down up to 20K. Yeah, so this means that this module, this VCF, is you can conceive of it not just as a gain stage, more of as a multiplier. Yeah? However, you can also achieve what I have here. It's a rectification. So if now, instead of combining a DC voltage and an oscillator, I will combine two oscillators. Let's take another sine wave here. I'm supposed to hear this, not quite. Okay, so what I have now is a so essentially, now by putting one of the oscillators into the input and the other one into the voltage control, what I have is multiplying the two waves, which is ring modulation. So if you multiply your signal with a sine wave, that's ring modulation. And let's just briefly look at the effects of that. Actually, technically what you have is that if it's a bipolar multiplication, then it's ring modulation, and if it's a unipolar multiplication, it's amplitude modulation. And it has to do with the multiplication itself. Now what I see here is that I'm actually getting a decent bipolar signal. Let's just see if I can make this a bit more visible, what's going on here. Okay, so I get signal like this. My triggering is having a problem. Okay, that looks like it. Okay, so I have these two multiplied, and let me just get to a similar frequency for both. Okay, so what I wanted to show you is what happens to the spectrum of this sound. So originally I'm not sure this is gonna show very well, but it's worth trying. So here is my FFT of this signal. Is this working nicely? I might have problems with this FFT. Anyhow, I'll just tell you it's worth knowing that what you will get is sidebands, yeah? And what you also get is interference. So what I was trying to show is that if I have similar frequencies, that's one, and that's two, this one is a bit low. Yeah, so I have two similar frequencies now. Something's happening to my scope in the meanwhile. Okay, I have these two similar frequencies, and what you get is this beating. Yeah, these things happen when you multiply two signals together, and this will also happen if you just add them together. So now I'm gonna add them into the mixer, yeah? But you do hear the difference. Yeah? So this is now adding the two oscillators, and that was a second ago multiplying them. Okay? How are you doing? All good? How are we with the time? Shall we have a break halfway through? It's normally good to
25 to 8. Can I just go say as well, we've got a toilet if any are needing to go through this. There's a toilet just through there downstairs on the left hand side if any need to go down the road.
Okay, so let's keep looking at this interference. So what we have now is these two signals of fairly similar frequency, and the interesting thing is that what you will also get is interference between a filter cutoff frequency and the incoming signal. So let's try this. So now I'm gonna filter this pulse signal, and this is the low pass of this signal. So you guys should see it, hear it as well. Cool, let me get out of the FFT. Okay. So that's that, and then this is the first channel. Okay, so now I have a filter frequency, and what I can do is if I omit the input and crank up the Q, I can set it to a similar frequency to the input. And then what I expect to have is a bit of a funny thing going on. Doesn't really, okay. So you actually hear the beating there. It's fairly fast now. I can try to tune this such that so here what you have is that in terms of interference like that, what you get is that if the frequencies are close together, then you get a very slow beating, and if they're further apart, then you get faster beating. So if they're actually at the exact same frequency, you are supposed to have no beating at all, but this is close to impossible in a system like this. Okay, right, so we've looked at those things. Let me see what I was thinking. Any questions so far? Any ideas? Spectral response. Okay, so we've looked at the ranges of signals. Now let's look briefly at how you could describe the function of a module. So first of all, we have spectral changes, which means that certain parts of the spectrum are affected and certain parts are not, typically for filters. And then we have non-linearities. Yeah, so I'm going to go a little bit into non-linearities here, just because I want to show you the transfer function. So what the transfer function is, it is a way of describing the output based on the input. And essentially what you do is you plot the input voltages against the output voltages. So what you always do is you have horizontally you would have the input voltages and vertically you would have the output voltages, and what you have is essentially a plot that tells you, okay, if this is a modular system, we can go from -12, although this is unorthodox for most modules, to +12. So the output also should go from -12 to +12. And essentially what you would do is you would be sending each of these voltages in whichever resolution to the output and then plotting the output. Now if you have no change in the signal whatsoever, then you get a straight line like this. Yeah, this is your transfer function, your linear transfer. And what you get here then is essentially a plot of the response of the system. Now, if I was to send lower voltages than -12, for which I would need an external thing because this one cannot produce such voltages, then I would be getting a hard clipping here. Because this system would just stop at minus or +12 because of the rail power. Now, what happens is that this will tell me whether there are any non-linearities in the system, and the important thing to understand is as soon as I have a non-linear system, I will get harmonics produced. So that's the main difference between filtering and distortion, is that the filtering will only alter existing spectral components, whereas distortion will produce new ones. If I get this into clipping. Now the point is that in an electronic system there is no such thing as pure linearity. Nothing can be purely linear. So there is definitely some anomaly. So there is definitely some harmonics being made. So what I'll try to do is now measure this. Now, in order to produce a plot of the spectral response, of the transfer function, what I can do is I can send a sawtooth wave through a module. So if I send a full full amplitude sawtooth wave, what I can do is see how it responds to each of the voltages. And if I look at one period of this sawtooth wave, then I will get this kind of plot. So let's first just try to get a sawtooth wave. This is supposed to be a sawtooth wave, okay? And I can take a pretty low frequency there as well. So this sawtooth wave now, it is about plus minus 5 volts. And I might actually struggle to get the full transfer. Let me just see if I can do the trick of double amplifying it. I have another mixer here. Let's see if this one will give me a bit more gain. There we go. So that's just a bit more. I'm still not against 10 volts really. So what I can try to do now is split this signal into multiple inputs of the mixer. Let's see how much gain I can get. So now I have the same signal in 3 inputs, and there you go. You see? So that's typically one of those things that you really want to keep trying to understand truly what it does. So what you see now is essentially a clipping. Yeah, so transfer function. Now, obviously I cannot call this, it is the transfer of this mixer currently, yeah, because it's overdriving heavily. But what I really wanted to do is actually test other modules. Now what you see here as well is that my waveform is not quite symmetrical. You see that my lower bit is not clipping and my higher peaks are clipping. Let's hear if you have any ideas. How can I fix this? What can I do to this?
You need to attenuate it. Use a bias control or something?
Yes, so that's an important term that I normally don't use, but you will find it used, biasing. Yeah, so biasing is the same thing as offsetting. I normally use the term offset, which is essentially adding a DC voltage. So what I could do is I could subtract few millivolts, well actually maybe 1/10 of a volt or something from this. So I can do that by essentially inputting a DC voltage into another channel of this mixer. That's my prediction. So let's see, I have this level here, I need a bipolar thing here. That looks good. This doesn't look good. Let me just take this channel. Okay, right. So you see, I can actually now change the bias of the signal, I change the offset, and by doing that, you see I'm clipping different parts of this waveform. Okay, so if I now try to do this, let's try to get an unclipped sawtooth wave. Just a second. Bit softer. Okay, I'm almost there. Okay, this looks good. This looks good as far as unclipped sawtooth waves go. Okay, so now that I have a decent test signal to get to my transfer function, let's try to see the transfer function of different things that I've got here. Just a second, I need this. Okay. So this is my oscilloscope. So I'm gonna scope. Well, first of all, let's see just the basic low-pass filter, yeah? What do you guys expect from a low-pass filter in terms of transfer? Anyone can explain why am I seeing this? What would this be? So actually what I've got here is a filter that's resonating like hell. Let's see, can we hear that? What am I listening to? It is supposed to be this, yeah? Something on. This is how it sounds, yeah? So actually what you have is that this is a self-oscillating filter at this stage. So what you had is my transfer function with an oscillation on top, and if I decrease the Q factor, you actually see what's going on here. So on this filter I have an input drive control as well, and that's what you see. So I can actually stay quite linear for a bit, and then you see that the linear portion starts to curve, which is essentially my clipping. And you can probably say that it's not quite hard clipping. You see that the actual curvature starts to come through. So instead of a hard clipping like this, what I'm getting from this one is a soft clipping, because there is a slight curvature here and a curvature there. Okay, so that's the transfer function of this filter. If I increase this clipping, this input drive, obviously I am making it clip more. And then the interesting thing is that you will see a bit of the impulse response of it as well. This will be the next topic, but you can already see that if the resonance of the filter increases, now I'm increasing the resonance, maybe worth listening. You see that you actually get a kind of a sinusoidal response at the jump. And then if the resonance is high enough, then obviously it resonates through. But like this, I'm getting something different. Obviously I can change the frequency. And get these things going. So you see that in my transfer function I see two things. First of all, I see whether there is any clipping occurring, and second of all, I can also see filter type resonance happening. Yeah? Okay, so how about the impulse response itself? So or actually, let's stick with the transfer function for a bit. So we've seen a filter and a saturator essentially. Let's now look at a folding. So this is, well, you know what the original looks like. So what I've done now, am I doing the right thing? I believe so. So now I'm looking at a folding module, and now you start to see that actually this response becomes much more complex. So this is obviously the cycle. I don't find it extremely exciting sounding really, but you see that actually if I have my symmetry all the way down, this has two controls. Actually symmetry is in the middle here. This is the minimum folds. I can get potentially, yeah, here's a very small amount of folds. So you see, this is where my transfer is pretty much linear. It's worth noting, yeah, that when I say linear transfer, it does not presume unity gain transfer. Yeah? So if this line in a linear transfer is 45 degrees, that is unity gain. But if this line is, let's say, steeper like this, if it's still a straight line, it's still a linear transfer. It won't produce harmonics. Yeah? Or if it's like this, it is attenuating and still won't produce harmonics. So essentially, compared to the original one, you see I have attenuation here, but nothing quite radically happening yet. And now you can actually understand how this folding really works, because as I increase the amount of folds, you see that the gain is going up, and as the gain goes up, it overshoots a certain threshold and then folds back on itself. So it's potentially tricky to, what I would have to do, shall we try and get a decent plot from this? Because what I would have to do to get a proper plot is to get, first of all, this original sawtooth here. Let's make sure it's straight, yeah? So this is the input signal, and then I would have to get my trigger to source from the second channel, so we get a kind of a fixed trigger. Just a second. Here we are. Okay, so now I've managed to fix the waveform. So the bottom one is the input, the actual sawtooth wave, and the top one is the folding. So you see, as I increase the gain, you see what starts happening. These are very small variations. So actually, at the first stage, I get a bit of soft clipping, and then slowly, I will get this fold in there. So essentially, you see now that I've doubled the frequency of the incoming signal, and then I'm going to get another fold in there, tripling, quadrupling, essentially increasing the amount of folds in the middle. Yeah. So this one also has stages control. So this is 2 stages of folding, 3 stages of folding, 4 stages. Yeah. One funny thing is you see that the peaks here are actually becoming smaller. Okay, and then I have the symmetry. So what I can do is essentially take these folds in and out. Okay, so let's try to think. Okay, what does this transfer actually mean? What is happening to the signal? Where am I truly distorting it? Actually, I'm distorting it in 2 ways. So the first thing, which is quite obvious, is that the peaks are being chopped off. So I have sufficient amplification there, and then I chop off the peaks. But what is this thing in the middle? Any ideas? What does it actually mean that we have a little bit of a sine wave there? It is actually a distortion that does not work on the peaks of the signal, because we have that already. Yeah, so it's not working on the peaks, it's working here. So what you actually have here is a kind of you know, if it comes close to the 0, the input frequency, then it does a very radical jump to -12. Well, not necessarily 12, but to negative voltage, to positive voltage, to negative, to positive, to negative, to positive. You see, that happens, all of this huge jumping, because you can see it here, happens just when the signal is at 0, just very close to 0. Yeah? And this is typical for some amplifiers. People call it zero crossing distortion, or there is another name, which is crossover distortion, which is a bit funny term because we use it for other things. So essentially you get distorted from both sides, so to speak, so very small amplitudes and very large amplitudes. And this is quite interesting, because what you have with distortion, is that you produce harmonics. And let me just see, maybe we can get a nice FFT from this. Okay, so this is now channel 2, and this is channel 1. So you get some kind of, I can probably get this to zoom nicely. Let's see. This is okay. So this is now channel 1, and this is channel 2. So this is your clean, and this is your folded signal spectrum. So what you see is that you're actually producing harmonics, and what happens is that normally with saturating distortion, with clipping distortion, you produce harmonics for transients. Because if you have a signal that starts loud, dies off, and you put it through a regular distortion algorithm, essentially what you're doing is you're messing up the transient. And the transients themselves are already broadband signals. It is the broadest, it's the widest band you get in a signal, especially percussive signals. So you really lose the quality of a transient if you distort your signal like that. Now, if you distort it close to the 0 crossing line, like we do here as well, then what happens is that you get the harmonics in the decaying portion of the sound. And this is really crucial because it will give you a colorful decay. And actually what you could say, what I would like to have normally from a nice distortion is something like this, where the actual loud dynamics are unaltered. Yeah. So actually, what I have, it might be a bit confusing, but you potentially will, you know, get to understand how to read these plots. But in essence, these bits, this bit here and this bit here, are the loud bits of my signal. Yeah. And you see that actually the loud bits are intact. There is a linear transfer where the loud bits are. Yeah. So this means that my transients, well, obviously the transients also go through a zero crossing, so they will not stay clean like that. But I will definitely have a much more balanced kind of induction of harmonics in terms of the input dynamics. Okay. Cool. Right. So let's look at the transfer of a few more things here. Just because I got this nice signal finally. Yeah? So what I have here is a pulse width modulation generator. Yeah? So what it does from a triangle wave, it is supposed to give me a pulse width modulated square wave. I assume you know what is pulse width modulation, but just for the sake of clarity, what happens with pulse width modulation is that you have a square wave, and the period of this square wave remains the same, so the pitch is the same, but what you do is you move this middle line, so you could get a signal that looks like this on one hand, and if you move it the other way, then you would get a signal that looks like this. So that's your pulse width right there. So when you modulate this, well, you can get interesting effects. We will also look at what it does to the spectrum. But let's just first check out what this pulse width modulation actually does. So it is supposed to create a square wave, you see, from a triangle. And this is what it does. Okay. So what do you think? What is the spectral response of this process? The interesting thing that's happening here is that, well, let's hear it, maybe that helps. So I'm gonna make the frequency a bit higher. Just a bit higher. Okay, here you can see it. Yeah? So actually what I have is that if my square wave that I'm just producing is symmetrical, which is somewhere here, then I have no even harmonics. And if my square wave is asymmetrical, if I get this pulse width happening, then I change the balance of the harmonics and I introduce the even harmonics as well. As I'm changing the pulse width, you see that the different harmonics are popping in and out. I get different balance of things. Okay, so from this, can we predict what it will do to a sine wave? So let's just look back at our plot here. So we're not listening, I will lower the frequency back again. This one. Okay. So what will this do to a sine wave? Let's see, can we predict that?
Does it introduce harmonics into it?
Yeah. In terms of the plot, what kind of waveform do we expect? Well, if you think about it, what does this actually do here? This is essentially a comparator inside, and what it does is I'm changing the voltage of the comparator, and what I get is like a true-false output. Yeah? So essentially what it's doing, I'm changing a certain voltage here, the second input to the comparator, and I'm saying, okay, now it's above and now it's below. Yeah, that's essentially what's going on. So if I do this to a sine wave instead, you see, I actually get pretty much the same thing. The main difference here is that I've lost a lot of range. You see, now this is the full range that I have, whereas with the sawtooth I had much more range. Yeah, because the comparison voltage is here, the minimum one, and for a sine wave that was much earlier on in the cycle. Yeah? Okay, how about the triangle? Here's a triangle. I think I remember that it was meant to be used with a triangle, but you see, actually the triangle gives me still less of a range than the sawtooth. You see, with the sawtooth I can get it this close, this narrow, you could say. Okay. Cool. Shall we take a short break? Yeah. Is it
5 past 8?
5 past. Okay. Let's have 5-10 minutes break, and then we'll take it from here. Go.
Oh yeah.
You want to play one of your sets?
Yeah. Just to them. Just downstairs, alright? Downstairs on the left. You're planning to finish up about 9 then?
Yeah.
I was going to shoot off and let Ben, because Ben's coming back to lock up because he's got half the module as well, because he's doing his session thing. I'll just figure out.
Yeah. Well, obviously you can go.
Yeah, no, it's not the same, it's actually quite, I'm actually learning a lot myself, to be honest.
Oh yeah? Does it?
Yeah, a lot of that I'm not aware of, to be honest.
How is it for you guys? Am I saying too much stuff you know already, or is it?
Yeah.
It's actually I've got the level, yeah. Hopefully, a bit over, a bit.
I'm a bit under, but.
Oh, a bit under. Actually.
No, I'm a bit under.
Yeah. But just by looking, I thought you'd be you're actually understanding everything.
Like 70%.
70%.
Yeah.
Well, that's the point. Actually, as far as my plans go, there is one more thing that I wanted to look at, which is impulse response. But if you can formulate a question, that's great, you know, and interrupt me, you know. I'm here to serve you like that. So if something is not clear, guys, please do, because we'll just finish early and go for a pint instead.
When you're talking about the pulse width, then the different waveforms,
Yes.
is it possible to achieve more the spectrum of your pulse width because of the amount of harmonics available within the different waveforms of your...
Reset. Say that again.
So, like you say, the saw wave, you've got more breadth in your pulse width.
Yeah.
Is that due to the, because obviously a sawtooth has more harmonics than...
No, it has purely to do with the transfer. You see, because essentially what I have is cheers, man. That wasn't mine actually.
What's yours?
1, 2, 3, 4, 5, 6, 7. Yeah? Cool. Német. That's a Hungarian surname. Huh? Beszélsz magyarul?
I can't speak it. My family can, but I can't.
Oh, there you go. Maybe you have a sister who does?
My mum.
Oh, your mum. No, I'm not there yet. Yeah, so what's happening here essentially is that, you see, you have the input values. As we do, we plot them on a horizontal axis.
Yeah.
Yeah. And the way this works is it has a single threshold. You see, now I have this dropping sawtooth wave. I could potentially make it right way up. Looks like I can't. Anyhow, so what happens is that, you see, at this point in time where this flank goes up, oops,
Yeah.
it's not a permanent, yeah, so I can probably draw as well. This is the point where it flips the decision. So essentially what you have is a decision-taking thing, a comparator. It says, are you larger or smaller, yeah?
So quantizing, so...
It is a sort of a binary quantizer. Yeah, you could call it that, yeah? You see, so at that point it does it, and if I change the control, you see what I'm actually doing is I'm changing the voltage of the comparator, because it's still doing this single decision, is it below or above? Now the reason why this pans out differently for a sine wave is that the voltage is the same, the threshold voltage is the same, but you see the shape of the sine wave?
Yeah, yeah.
You see that actually that voltage is much later.
Yeah, yeah.
Because they're all kind of bundled up here, so I have much less resolution, I have much less chance to get close to the top.
Right.
You see?
Yeah.
That's the thing. Does that make sense?
Yeah, no, that makes a lot more sense.
And actually the funny thing is, if you see what I'm doing now, actually it's a pity you don't see it, but with the volume, so well, you don't, let me just think if you can. Well, you're supposed to see that sine wave actually, but is it so minute, the change? I'm wondering. So what happens if I decrease the volume of the sine wave, then I can get to that range.
Right, yeah.
You see?
Yeah.
And now it's all true. Now I'm actually, you know, I've dropped the sine wave enough for it to be out of the range completely, so I lose the whole oscillation. So I can actually get to these very you see, I can still hear it. So now I've got the littlest range possible there, but with the sawtooth, I'm still okay at this voltage. You see, I actually have a finer control in that top range there. Okay? Make sense, yeah? Cool. Any other things to clarify from the first half?
So is that comparator working in, how's that working in the analog domain then to distinguish different values?
I wouldn't know the electronics behind it. Comparators are mostly, as far as I know, in integrated circuits. I think you can make a comparator out of transistor one way or the other, but you know, it beats me. One of the interesting things would be here to see if we have, again, kind of a limit in the high frequency range. Yeah? So if I now, let's keep listening to this, if I increase the frequency here, it does. So you could say that actually at about 3K, well, that does sound a bit higher than 3K. It does read 3K, but you see that actually at a certain point, let's zoom in. What happens is, this comparison is lost. Although it might be that the amplitude has gone down. Well, let's test for that. I hope you like this sound as well. Yeah. So it seems that actually it was that it doesn't really have a problem with high frequencies. But that's the thing, most of these electronics, you know, would do pretty much the same thing in megahertz range as well. I mean, you know, typically electronics work for radio frequencies, you know, so that's the thing, they don't really have this higher limit. Some things do, actually. I have like an offset attenuator, which just freaks out at about 3K. Just doesn't send the signal through at all. Any other things? Okay, so shall we look at the... I do actually have a ring modulator in here as well, because essentially I think you've mostly seen the plan for the course, so we're gonna get into other into types of processing, many types. For example, what I could measure, that's an interesting one, just to show you this kind of frequency top that you sometimes have. This is now the, hopefully, let's see, the trigger, yeah, it looks like it's triggering. Let's see. That was a good break, wasn't it? Yeah. Okay, so I need range, sustain, attack. Oh yeah, now I'm actually beyond the frequencies that it can take, probably, that's why. Okay, here we are. So what I'm doing now is I'm driving an ADSR, an envelope, with this sawtooth wave. So I could be getting a nice little thing there. And just to show you that what is the frequency now? It should be 63 Hertz. Let's see if that makes sense. So now I'm listening to the ADSR that is driven at 60 Hertz. So I'm using it a bit like an oscillator, or actually a wave shaper, I should say. If I play with these parameters, I might get something. Obviously, if the things are... This one actually has two ranges. So in the lower range, I have more of a thing. Well, the sustain doesn't do much, likely because as a gate signal, this one is problematic. Maybe if I do a pulse width signal instead. Let's see if I can get... just to get the nice little ADSR shape in there. So that's sustain, release. Okay, okay. So this is the... there we are. Something like that. So you see the sustain is not huge, but I actually have a little bit of an ADSR shape. And I can check how far I can go in frequency with this. So that still works, and that already doesn't. So it breaks here, and you know when things break, that's when they start to sound interesting. Now obviously if I take down all the time parameters, I should be able to get higher frequencies. Let's just get... okay. So here we are. Oh, no, actually no, you see? So no matter the fact that my envelope is sufficiently short here, you see the envelope is actually already finished. As soon as I cross this frequency of about, well, it reads 300 Hertz, realistic? 300? Could be. You just can't rely. Actually, the best thing, obviously, is to look at the divisions. So what I have here is one cycle takes 1, 2, 3 divisions, just slightly more than 3 divisions, yeah. And one division is 1 millisecond. So let's say 3 point something milliseconds. Yeah. So that would be about 1 over that. So 300. Something like 300 hertz should be about it. Yeah? So you see this envelope generator just stops responding when the trigger is above 300 hertz. But it tells you that, okay, until that frequency, it might be doing some interesting things. We can check this one out. I have another envelope generator here. Let's see how this one will cope. Okay, so you see this one already, I now have my time at the minimum settings. It seems like it's still doing it. I have a comparator in here as well, actually. So I can make a similar effect. And now, let's see if I increase the further frequency. You see, so this one actually allows me. Okay, well, it did break at some point. Oh. Yeah, so that's still alive, seems. Still didn't quite kill it. That's where it really breaks, seems. Okay. So that's already 1.7K. Yeah? And you hear that it is breaking. There's something going on. It's not just a... I mean, this is essentially a deterministic thing, supposed to be. If you do this with a digital computer, you will not get any of the intermittence. It will be just a buzz, because this is now technically just a fixed waveform. There is nothing changing about this signal, but because it's electronics and we are abusing it, it's breaking. Yeah, that's what's going on. Okay, so you see this envelope is already really different from this one. I mean, now I'm actually looking at the comparator output. If I look at the actual envelope output, you see I get this, because actually that becomes just a very small triangle wave. I'm just losing a lot of volume there because it doesn't have the time to go up and down. But the comparator output does something really funky like that. Okay? Cool. While we're there, we could also have a look. Let's see how this one does for frequency response. So what I've got here is a slew processor. I'm going to have a class around these as well. Essentially what it does, it limits the slew, essentially the gradient, yeah, so the steepness of the function. So now I'm sending it this pulse width modulated signal, so the bottom one is the input, yeah? And then from the slew generator I can actually control, hopefully, let's take an exponential one, the kind of the bend of this waveform. I'm a bit surprised it jumps like that, to be honest. Okay. See, so I can actually change the shape. Obviously this will produce some kind of timbre change. Now I'm running at a really high frequency, so that was the point. Let's see. I expect this one to go much higher, honestly. See this one? Okay, so that's pretty much the top of this oscillator's range. So you see, actually this slew limiter doesn't have a problem with 10K at all. Okay, let's see. Well, obviously I don't really hear timbre change at that point. Okay. So what's fun? Well, the fun thing is, I don't want to verge off too much, but the real fun thing is if I take the output of this slew limiter and use it to control it itself. Let's see if that will produce some funny anomalies. Might not, but it could break. I'm not seeing the output now anymore, so let's see. Okay. You see, so essentially with the feedback in there, I'm just using it to control. There's many CV inputs here. It allows me to morph this shape. But there was one question that I asked previously and I didn't get to talk about the second option. So the question was, what do I do if I have DC offset? So DC offset can be dangerous. You can burn amplifiers, speakers. Probably good to say, you know, in general, don't do this with volumes full on. Yeah, especially if you get into experimenting with stuff, things can break. Especially with very low frequencies, with DC offset, you can have a problem because what it does, it keeps the cone of your loudspeakers sticking out, which is tons of power, and it just can burn easily. Or the other thing that can happen is that you can drive your tweeter with frequencies that you can't even hear at very high volumes, and they burn as well. In 2017, I've burned 2 tweeters in Bristol venues. So you should be more careful than I am. The thing about DC offset is that you understand it's a 0 Hertz frequency. So what I can actually do is I can do a high pass filter at 2, 3, 4, 5, 10, 20 Hertz. And actually high pass filters at these sub frequencies work really well. They almost scoop up the energy from the range where you wouldn't be hearing anything. So it's always actually in my main live rig I have just a special filter which I use only for high pass at these low sub frequencies, which is always in the circuit. I wouldn't want to play a set without it because it's dangerous. And second of all, because it really allows me to kind of control the bottom end of things. So depending on the venue, how large the woofers are, always scoop it up. Always make sure that you get most out of the system. So let's try to do that. So what I have here now is, let's say, a heavily DC offset signal. So now I've been looking so far at the input signal, so I'm not going to look at that anymore. Well, this was the trigger. But instead, what I'm going to do now is, let's see, I'm going to do this high pass filter trick, okay? So let me just set that up. So this was my output from there, which, oh yes, I had this feedback thing going on, so I'm going to remove that. Okay, and get this into a filter. Right, and then the output of that filter is what I wish to hear, or at least see. As far as the sound goes, it's unlikely to give you a huge difference. Okay, so here you see I have this DC offset waveform. So now my input is top and my output is the bottom. So let's play with these frequencies a bit of. So you see that actually Well, actually, it's not even perfect, really. But you see, what I'm doing now is I'm changing the cutoff frequency. So at this stage, I have only the high frequencies, and then more and more lows. So what you see that, I don't know if you see the arrows here, but actually the 0 line is the mid of the top half for the first channel, and it's the mid of the bottom half for the second channel. So you see that the actual input signal is unipolar. The bottom half is also positive, larger than 0, so it's all the way up. And then the high pass version of that signal is more or less centered around 0. Actually, if you really want to be accurate about understanding DC offset from the plot, it does not have to do with the peaks. So it's not about whether the peaks are equidistant from the 0 point. It is about the energy, and the energy of the signal is the surface that it encloses. So if I have a, so let's take example this previous. So if I have something like this, you see, so this is the 0 line. You could say, well, it looks like a DC offset signal because the top peaks are much higher compared to the low peaks being low. But actually, if you look at the amount of surface that you have in the positive half, should be, if it's no DC offset, and there's probably none in this stage, then the surface are equal. Because this is a very narrow peak, it can go higher, and because this is a broad one, it doesn't need to go as high, it will still have the same amount of surface. I mean, if I zoom in a bit, maybe you see it, So technically, this is the 0 line here, so the surface of this little peak should be the same as the surface of this thing below. So actually, very useful technique, killing DC offset. And you see, if I actually have those peaks similar than the bottom peak goes, actually I can do it the other way around as well. Does this sound any good? Probably not, So this is a story about how the cool looking waveforms sound like. We are listening to the bottom waveform, I believe. Oh no, actually we are not, sorry. My mistake. We are listening to this instead. So let's listen to the actual bottom waveform. That's more like it. Obviously now I'm not seeing the other waveform either. Interesting thing to know about waveforms is that historically we have this idea that waveform explains, the sound, it fully describes it. The thing about waveforms is that a single repeating waveform is just a buzz. No matter what you do to a waveform, if you keep repeating the same waveform, it is a buzz. So the interest in terms of sound comes from changing the waveform, from the way how it changes. And you can make that happen in many ways. I mean, when a module starts breaking, then obviously it changes things in different ways. If you use a folding or other kind of nonlinearity, then what you get is that the waveform changes based on the dynamic. So as long as it changes, it's fine. The other thing to know is that if I have a mixture of sine waves, well, I think I cannot demonstrate it here, I don't have a delay in here. But if I have a mixture of sine waves and I change the phases, which means I change the relative delays of each of these sine waves, my waveforms will be looking very different from each other, while the sound is exactly the same. So you could say that there is some link between the waveform and the timbre, but it's not as direct as people used to imagine 100 years ago, and which still kind of lingers on this kind of waveform idea. It's like the myth, because it's all about changing the waveform. And another thing worth knowing is that if you have a repeating waveform, so actually this is a good example for that. you see, what I have here is essentially only harmonics. You see, that's the thing which is not necessarily easy to understand, but what you get is that you cannot squeeze in a spectral component, a frequency, into a waveform that is not an integer multiple of that fundamental frequency. Because in a way, you see, the point is that if whatever I do in a single period, so let's say this is my basic period and this is the fundamental frequency corresponding to that time duration. So whatever I do to this waveform, if I keep repeating this exact same waveform, it actually means that I've done something with the harmonics. There is no way of detuning this harmonic, so to speak, just by changing the waveform that is repeating. This has to do with the Fourier series theory. And it's worth noting, because actually what would happen, for example, can anyone tell me if I was to actually detune one of the harmonics?
It's going to be more evident. That one's going to be more evident.
It will be more evident audibly, but in terms of the waveform,
It would be a sine then.
no, what would happen is essentially I would get a changing waveform already. You see, because if this frequency suddenly does not correspond to this duration, but instead corresponds to this duration, so I've detuned it slightly, then the next time it goes around, it will actually end here, and then end here, and then end here, and then end here. Because, you know, if I juxtapose two different lengths and both are repeating, they will be coming in and out of phase. Does that make sense? So actually, if I detune, if something is not a pure harmonic of the fundamental frequency, then already I will get a changing waveform. It will make for the fact that the waveform keeps changing. So you can actually get interference. So what you've seen with two closely tuned sine waves, in terms of producing a beating frequency, a non-existing frequency, so to speak, you can get the same effect from a harmonic as well. Yeah, you can actually, because you see, that's the point. If you have, well, I didn't go necessarily into the basics, maybe that's a thing worth ending with as well, is that, you see, if I have a sine wave, let's see. And another sine wave very close by, so let's say this is 100 Hertz, this is 105 Hertz, and I mix them together, I will get a 5 Hertz sine wave. But let's actually look at this, because that's quite interesting as well, because we've looked briefly at multiplying two sine waves and adding them together. You've heard in both instances we had this really low frequency popping up that is equal to the difference of the two frequencies coming in, but we had a distinct timbre from that, definitely. And one thing that is worth knowing as well is that if I so let's start from there. So if I distort just a sine wave, I have a sine wave. This is the spectrum of the sine wave. If I distort it, let's just say clip it. I have this soft clip here that I'm going to use. What I'm going to get is harmonics. If I have another sine wave close by, I will get the harmonics of that sine wave as well. But I will also get intermodulation frequencies much louder. So the intermodulation distortion, so the point is that all these new sine waves that happen, yeah, will be harmonically related to the originals, which means that perceptually they fuse. You don't really hear them as separate sine waves. But if I take two sine waves like this through some soft clipping, then I will make the intermodulation harmonics louder. And the intermodulation, sorry, not harmonics, intermodulation frequencies are not harmonically related. You see, because they have to do with the difference of the two signals. So these are the intermodulation frequencies, and that is potentially useful if you want to create kind of alien harmonics. Yeah, typically we have other ways of doing this. We're going to look at this in more detail at some point, but let's just try this to start with, okay? So I'm going to do a completely open low-pass filter here, and then what I'm going to do is I'm going to mix in two sine waves, okay? So this will be my output, okay, low pass, and then this will be my input. Where the hell is this one? So what I'm gonna do is mix two sine waves. Well, actually, worth showing you possibly as well. I mean, when I look at the module with an oscilloscope, I discover that they're all broken already. I mean, I've bought a lot of second-hand modules myself, and it's like, okay, I'm playing with them, everything does something, and then I do measurement, I'm like, this is broken, this doesn't work, this is wrong, and which is great for me because I don't want it to be surgical, you see. So worth showing you possibly is that this sine wave, okay, let's have a full-on sine wave here. Huh. Does that look like a sine wave? No, it's filtered like that. Let's decrease the drive. Yeah, it looks a bit like this. Sounds a bit like this. Okay, doesn't sound very clean. And it doesn't even look symmetrical. You see, you actually see that it's wrong. And now I compare it to this sine wave. Which also looks quite wrong, although I must say that it used to give me another funny glitch as well, this sine wave oscillator, but now it's fine. Or was it this one that was problematic? Okay. So yeah, they're not even close to sine waves. I mean, in an analog circuit, it's really difficult to get a pure sine wave. What you normally have is an adaptive filter in there. So a filter that is supposed to cut off all the harmonics, which is obviously far from perfect. And then you have certain wave shapers. I have one, but it's not here. But what I wanted to show you is having two sine waves.
Alright, cool. How'd it go, alright? Fine, no bother. Cool.
Okay. These are two sine waves. Yeah. So you see something funny is going on there already. And actually, if I have the sine waves only, I hear certain beating. But if the frequencies are far apart, then there is none of that. And then what I will do is now I will increase the saturation, the soft clipping. And you actually hear that there is completely dissonant frequencies coming in. Yeah? So compare this. So the point that I'm trying to make is that this distorted sine wave, yeah, and this distorted sine wave, if you distort them together, you get the intermodulation frequency. You see, so it's not just the sum of these two things. through nonlinearity, what happens thus is that you get increase in intermodulation frequencies. You see, so if I don't have two of these soft clippers here, but if I was to do that, if I was to soft clip one of them, soft clip another, add them together, I would get a clean mixture. But if I put them together into soft clipping, then I get all these other things as well. Yeah? So it's not this plus this only. You see, these are clean sounds, there's only harmonics to them, but you get all these intermodulation components as well. Yeah? So that's typically what, you know, makes your sound kind of funky. And the thing is that, you see, actually you would say, oh well, that's irregular, that's out of the ordinary, but actually the sine wave is out of the ordinary, and the mixture of sine waves is the ordinary. You see, because we hardly ever, this is not a true sine wave anyway, but if you are distorting you know, an acoustic sound source or a more complex sound source, you already have multiple components. So that's why you're already creating intermodulation artifacts. Whereas only with sine waves, which is the special case, a single sine wave is the special case, then obviously there is no intermodulation, you get only pure harmonics. Okay, cool. Was that kind of clear? Anything to add, subtract from this? Non-linearities, asymmetry. Well, I've pretty much covered most of the things. So now we're down to wish list. Make some noise. What's the time, Martin?
1:15.
1:45. So yeah, we have quarter of an hour. We can try to make some serious noise, or try to make some further analysis of modules. Oh, actually, let's do this. Let's do this one, because I think some of you will be here on Friday as well. And on Friday we will do compressor building, so we're gonna build our own. But I have here a ready-made compressor, so to speak. And I haven't prepared this, but I shouldn't have a problem with demonstrating how to test the compressor. Yeah, because what you get is an interesting behavior, and none of the current tests have shown us that. Although now I'm reminded that there is one more testing procedure which I wanted to show you, which I didn't, which is impulse response. So maybe I'll leave this compressor testing for Friday, because it will be more timely then. Let us just first look at impulse response, see how much time that takes. So what is an impulse response? First of all, it is the response of a audio processor to an impulse. What is an impulse? An impulse is a very sharp peak in the waveform, a very sharp peak in voltage, or as far as the speakers are concerned, a very quick excursion back to equilibrium and stay there. Yeah, that is an impulse. So it is a really rapid burst of energy, you could say. Now, important to know is that an impulse has a broadband spectrum. Yeah? So we haven't covered much of this. I sort of, you know, it's the intermediate course anyway. So what you have is that a sine wave in frequency spectrum is a single line. So if you're plotting a spectrum, this is frequency, this is amplitude. And the funny thing is that this is the narrowest possible spectrum that we have, a sine wave. It is the cleanest, the purest signal. Yeah, that should be something you understand. Now, if you look at the waveform of the sine wave, actually it is infinite. So what you get is this funny oddity that the narrowest possible thing in spectrum is the widest possible in time. Because, believe it or not, what happens, if my sine wave lasts for 1 second, well, it's a fairly pure sine wave. If it's 1/10 of a second, it's already not a pure sine wave. It's getting a skirt, so to speak. Yeah? If it's 100 cycles, then it's even more of a skirt. Yeah? If it's only a single cycle and then it's all 0, then already I have a spectrum which is getting to be more flat. Yeah? And when I get to the other extreme, so that's the funny bit, if I have a waveform which is amplitude over time, if I have an impulse in time, what I get is, so to speak, an infinite signal in frequency. You see, so there is this duality. These are, you could say, the two ends of the spectrum. So an infinitely long in time sine wave has a unity, has an impulse for its spectrum, and an impulse in time has an infinite spectrum. Yeah, that's this funny thing. So it's worth knowing that impulse, therefore, can be used for signal testing. What is the other signal which is flat in spectrum? You guys know?
Noise.
Noise, yeah? So the thing is that an impulse has a really reliable spectrum. You know, if you keep sending impulses, it's the same thing all over again. With noise, what you get is, you know, slightly varying spectrum. There is a lot of fluctuation. The fluctuation isn't great, isn't large, but it's nevertheless there. So as far as testing things go, an impulse might be a better choice. So how do we get an impulse? Well, I believe this one is fairly narrow if I tune it like that. There it is. So with this oscillator I can generate that. So now I'm gonna use the first channel of the oscilloscope to plot the, well, actually the first one is now the output, yeah? So the second one will be my impulse. Okay, let's do that. And then let's just hear it as well. Okay, so if I can try to get the narrowest possible impulse from there. And if I actually want to test the impulse response, what I'm likely to do is take a much lower frequency as well. Because an impulse actually does not necessitate a period like that. You don't have to have a period involved. Probably get even lower. See? Okay. So this is typically, you see? So my impulse is not really perfect. You see, I have this flank here and then it goes back again. Oh, now I've lost it. And you hear how the amount of low frequency changes based on the impulse width. Okay, so this is now the second channel is my input, and then so the lower one is the input and the top one is the output. And now I'm gonna look at the impulse response of a low pass filter, and that's what's happening. So let's just get sorry, the position, I can probably modulate that, yeah? So this is how it sounds like and this is how it looks like. So it is worth understanding that actually low pass filtering, what it does to a waveform is it makes it smoother. Yeah, that's fairly important. So that's the kind of thing that you can really use well, because there's other ways of making a waveform smoother as well, which are not necessarily called low pass filtering, but they still do the same. And we've seen two already. So you saw my slew processor, my kind of gradient limiter, yeah? Which what it did is it made sure that there are no fast jumps. It kind of smooths out the fast jumps. So actually that's a low pass filter as well, yeah? My ADSR that worked, this one worked up to, what was it, 3 kilohertz, and this one went up higher, something like that. These are also low pass filters, essentially. They're not made to be, but through the fact that they will do the same thing, you see, they will smooth the waveform out. they're supposed to do this. So let's see how that happens. Okay. So now I'm gonna take my ADSR. Okay. Would that work at all? Let's just see. I think I might not be. Is it triggering? Just a second. It might be. It looks like it's not really taking this impulse. Okay. Now it is. So you see, now I'm just sending an impulse through this. Let's see if we can observe what's going on. So you see, this is the input signal, the lower one. This is the output signal. So by making it a smoother wave shape, I get a kind of a low-pass filtering effect. I think I can still... Right, now we see the whole cycle. And this is a funny thing. You see, now that my attack time is longer than the period duration, I'm actually having an impulse. I'm losing each impulse. So you see, it doubles the frequency there. So my ADSR is actually a low-pass filter. Then my slew limiter, similar thing. So this is an impulse going in. See? It's a low-pass filter as well. Can't necessarily see it always on the waveforms. But that's the impulse response of my slew limiter, yeah? It's a bit funny. I don't really get to... Oh yeah, because this is the rising flank, yeah? And then this is the dropping flank. But the point is here that you see the waveform starts to drop only here and it immediately starts to rise. So I don't really have much control over this phenomenon with the lower flank. So if I increase the bandwidth, the pulse width here, you see now I can actually get this flank also to respond. Okay, so that's the message. That's a low-pass filter as well. So everything that will make a waveform smoother is a low-pass filter. Now, how does the impulse response of a high-pass filter look like? So here is a high-pass filter. Okay. And what you see here, actually let's make it first more of an impulse, potentially actually like this. Okay. So what you see is that from a strictly positive jump and a back to zero jump, that is the input signal, if I have a high pass filter response, what I have is a rebound. I actually go far below the equilibrium as well. See, so that's the thing here. Whereas with a low pass filter, obviously the only thing I had is a kind of a smoothing job. Yeah. So it's I never get voltage that goes below the equilibrium. Yeah, it's always on top, just like this one. The only thing it does is sort of makes it slower like this or that. But with the high pass filter, what I get is indeed this kind of going to negative moment here. So what that actually does, if you want to think about this in terms of, you know, common language and kind of describing what we see, what it actually does, it makes this little corner, so this is a fairly sharp corner, it makes it even sharper. You see, so from a corner that goes only up, which is a lot of high frequency, yeah, it adds more high frequency by making it drop down as well before coming up back again. You see, that's what happens with a high pass filter. So as far as coming up with, you know, other modules that do high pass filtering, I'd be puzzled really if I could find any that produce this kind of impulse response. Yeah. And then finally I have a band pass filter here as well. And what you have with the band pass filter is, you see that you're actually changing the Now I'm increasing the resonance as well. So essentially you get a bit of a sine wave as a response. If I have, and also if I have no resonance there, I would still get a little bit of a sine wave in there. Just get a bit louder. So what you see here actually is that I have both things happening. So one thing is that it did make it smoother, so it's not as sharp. And the other thing that happens, it did go below the equilibrium as well. Because obviously band pass filter can be made out of one low pass and one high pass as well. So you see both of these effects. Yeah? Now as far as the impulse response go, you might have seen this term in reverbs, yeah? Because impulse measurement is really useful for getting a measurement of an acoustic space. Because what you will see, I mean, these are really simple electronic impulse responses, but if I was to take the impulse response of this room, then I would get a lot of similar impulses, which would be reflections, and you would get a kind of a reverb tail thing. So you would get first a very let's say a few reflections, the early reflections, and then you would start to increase the density of reflections, and that would describe an actual room that reverberates. Yeah? And then with the digital system, what you can do, you can create essentially a filter that will behave like the room. Yeah? Because you see, the main difference here, so what we kind of discovered, I hope, is that filtering and actually reverb are linear processes. Yeah? They will not introduce new spectral components. The non-linearities will. And a room typically is not very non-linear. I mean, there is some non-linearity to the air transfer, but it's really difficult to measure. It's very small. But the room typically isn't. So actually, to model a room, all you need is a very complex filter. Because you see now that what you consider a filter to be in terms of, you know, changing the balance of high and low frequencies, that's fine, but people mostly omit the fact that it can have a tail. You know, it doesn't go to say that the filter will just change the balance of frequencies in a single time instant. Yeah? If you hit a filter with an impulse, especially if it's resonating a bit, you see, you get a whole waveform behind it. Yeah? That's what happens. Yeah. So actually, you could model a room with a very complex filter, and an impulse response based reverberation is technically that. However, most often it's implemented through FFT because it's cheaper through it's less CPU intensive. Okay. Questions? There must be things that weren't quite clear. Something we could discuss. We can discuss it over a pint in the canteen in a minute as well. Probably saturated with signal processing by now. Okay, cool. Well, thanks for coming, guys. We're on time. Yeah, it's about 9.
1 minute past.
1 minute. Timing. Yeah, I started as a drummer, and I recently got an acoustic drum kit again. I didn't have one for 15 years, and now again. Cool.